Okay, today I'm gonna redo the video that I did as a short with the knots realized as embedded loops on a union of 4 orbifolds, or Math-Cal-I, interface construction. So we're gonna look at knots looping around this interface construction. So let I, Math-Cal-I, the interface construction, be a subset of R3. And let's take the union of S1, S2, S4. So these are our 4 orbifolds, the canonical shapes that we got from the optimization problem. So maximizing constant positive Gaussian curvature and, maximizing enclosed volume and preserving constant positive Gaussian curvature, where the cone points are embedded as antipodal points on the unit cube. So we got our 4 football orbifolds. You can think of these as American footballs, shaped objects, 2 cone points each. Each is homomorphic to the standard sphere. And we'll assume the following incidence data. So for all I not equal to j, we'll take the set C sub ij, defined to be the pairwise intersections between these two. This is a finite union of smooth one-dimensional curves. So nowhere do any 2 orbifolds completely overlap. They're in these sort of transversal positions in the cube, and so we only get 1D loci. So the common intersection of any 3 S sub I, these orbifolds, is empty. So we only have quadruple points, so 6 points where the 4 orbifolds meet at one single point, so they're on the edges, the outside parts, and they form the vertices of this graph that we're going to talk about. So the union, let's write gamma, defined to be union I less than j. So here we have the gamma. So this is the graph that includes, so this includes the union of all the pieces. We're going to assemble them together into a graph. And this graph is connected, embedded, 4 regular, multigraph. Technically it's not a graph, it's a multigraph, with 6, actually, sorry, it is a graph in this case. It's the outer portion of the entire graph, but it's 6 vertices, 12 edges, and each edge is a component of some of this, some C sub ij component. So I'm personally interested in studying closed curves that lie on Math-Cal-I. So I'm interested in these knots, so that they're embedded in R3. So Math-Cal-I is embedded in R3, so we take it away and leave the knot tracing through R3, and we'll get a classical knot embedded in R3. So now, a routed, I'll leave that there, a routed loop, so write this down, routed loop. This will be our knot object. The subset of Math-Cal-I. So this knot sits on the surface of the interface construction, and so it's like weaving in and out of the junctures, like through gamma, through the edges, but it's not crossing any vertices. So the conditions that can't cross any cone points of the football overfolds or quadruple points. So it has to go through edges and weave in and out like that, like a string or a ribbon. So a rad loop is a K subset of methyl I is a piecewise smooth closed curve such that each segment of K lies in the smooth part of a single surface S sub I, away from cone points and away from gamma, except at finitely many transfer points where it meets gamma. So these are the edges. At a transfer point, P is an element. P is an element of C sub ij. Take away the vertex set of quadruple points, then the curve crosses transversely from one orbifold to the other. It does not need to follow the C sub ij edges or components. So it doesn't go along the graph, it goes transverse to the graph and switches sheets with these orbifolds. So okay, so I said we'll call K admissible if the inclusion K is embedded into R3 is in fact an embedding, no self-intersections in R3. Okay, so this takes us to our a possible question we might ask is, can the first instance of a non-trivial knot, the triphylon knot perhaps, we realize that's an admissible embedded loop on methyl I, the interface construction? If so, how can one explicitly specify a path K such that whose embedding is isotopic to the triphylon knot? One way to look at this is, so one way to begin, we're not going to solve this entire problem yet, but one way to begin this is to say the methyl I is a symmetric object. We can embed it at the origin in R3, so the point 0, 0, 0, and then we can, so each cone point lies in a unique octant of R3. So we can put it in a general position, and then we can label the cells. So we can label certain cells as in a combinatorial way. So meaning like if the graph, I can't really draw the graph, but the graph sort of encapsulates, like goes across the outer portion of this methyl I, then we can label something like this. Spherical triangle where the cone point points out here. And say this is the positive octant of R3. So I'll just draw a cone point. Maybe it's that. Something like that. So it's protruding out, the cone point's out here. This is one edge, one component. C sub ij is one of the components of C sub ij. This one's another one, this one's another one. So we can label these combinatorial, sort of like the, pretty much exactly like the Grassmannian, positive Grassmannian. So yeah, that's just a start. I think if we do that, then we can have a way to track the knot, like label the knot in a way that's canonical or conventional. So, for example, if it jumped from surface, we label it plus, 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 and then we can have a sequence. So, like the surface pointing in the plus, plus, plus octant, completely positive octant, and then it jumps through an edge, so we'd maybe write that as like 0, plus 0 or something, and then we could get a sequence that specifies the knot on this complex, and then we could determine whether it's trefoil or not.